Hello everyone, welcome to today's lesson on similar triangles. So this lesson is pretty much the meat of this unit. Alright, so all the scale factors we learned pretty much leads up to the idea of similar triangles. So by definition, similar triangles have the same angles, right, and proportional side length. Right, we'll go over what that means in a bit. But their side lengths are proportional. And they have to meet both criteria. So this is the symbol we use, a single squiggly line. Right, so it might look familiar because this is the same, it's almost the same sign as the estimate sign, right? The square root of 2 is around 1.414 as an example. Alright, so it's just one of those squigglies here. Right, so if two triangles are similar, we use this squiggly line to denote it. Right, and to denote a specific triangle, we just have this triangle symbol with all the points as the letters. So triangle ABC refers to this one here with the points A, B, and C. Okay, so the ABC triangle is similar to DEF triangle. Right? DEF, 3 points. Okay, so they are similar because they have the same angles, also because I copy and pasted them and drew them, but also their side length are proportional. So whenever we see two letters like this in the context of shapes, we're referring to them as lines. So AB here refers to this specific line right here. Right? So we denote the two ends of the line and then just put the letters together. So AB is this line, and then DE is this line right here. Maybe I can illustrate it better with highlighter. So AB is this guy, DE is this guy. Right, so notice here that when they're proportional, it means that the scale of each of those lines are the same. Right, so as we can see, those lines are all different length. Right, but the scale factor between those lines should be the same as ACDFs. It will be the same as those two lines. And the scale factor between those lines is the same as BC over EF. Right, so the scale factor between all of those lines are exactly the same. And that's what makes them similar triangles. Okay, so let's take a look here. Alright, first of all, we can see right away that those triangles are not in the right orientation. Right, so let's flip it so it's easy to look at. Right, so look at the first triangle here. We have the 80 degrees at the bottom left and then 40 degrees on the top. So we can essentially kind of flip this triangle around. Oops, let's do a highlighter. We can flip this triangle around. That's a horrible triangle. Wow. Yeah, that's good enough. Right? Okay, we're just flipping it around so it's in the right orientation here. Okay, so now 50 is at the bottom left. So now this gets flipped here. The 50 degrees, as you can see, when we flip the 80 this direction, 50 degree refers to this angle right here. Right? Which means that the 2 is here, the 5 is here, 7 is here. Okay, so again, all I'm doing here is flipping the triangle, so it's easy to look at. Okay, and then from here, right, let's give them some names. Right, so this is corner A, B, C, and then this is corner D, E, F. Right, we give them names so then we can refer to the lines easier. Okay, so first step. Alright, let's check if all the lines are proportional. Okay, let's look at the scale for this one here. Got this line and this line here. So the scale of AB over DE is 10 over 2, which is 5. Okay? Now let's check this line and this line. The line AC over DF is 35 over 7, which is also 5, so that's good. So far, so similar. But this line down here BC over EF. You probably already tell where this is going. 15 over 5, which is 3. So as we can see here, all the scales are different, right? Which means that this is not a similar triangle. Okay, so not a similar triangle. And now furthermore, we can also check the angles. Right, we know this angle up here is 40. This one is 80. Right, and if we remember, the angles of a triangle is 180. Right, so what's this angle now? Alright, this angle is just 180 minus 40 minus 80. And we realize here, this angle here is actually 60. Right, so even though it looks the same, right, the angle is different. Right, which means that, and we know that in the other triangle, this angle here is 50. So it violates both of those clauses, right? We already know it's not similar if it's not proportional. But we also have to check the angles too. Okay, let's check this triangle now. Right, so it's a triangle inside a triangle. So when this happens, right, because those two lines are parallel, and remember those arrows just means those two lines are parallel. And because they're parallel, all the angles must be the same. Right? We know this angle right here of this big triangle is definitely the same as the angle of the small triangle. It's usually literally the same corner. And because those lines are parallel at the same level, where they cut through this line right here will always be the same. Okay, and then now let's check the length. Right, so we got a smaller triangle inside here. That's 4, 4, and 5. And a bigger triangle around here. Okay, once again, we'll give them some names. A, B, C, D, E, F. It doesn't actually matter what letters you give it. You can give it like X, Y, Z, whatnot, as long as you make it clear. Okay. So let's check those lines. You can see that A, B, and AC are the same, right? D, E, and D, F. So the proportion of line AB over DE, right? This must be the same as AC and DF, right? Those are literally the same numbers, right? 4, 16, 4, 16. Yeah, they're both 4 over 16, which is 1 over 4. Next, we check this one. BC over EF reduced to 1 over 4. Right, and as you can see here, right, we know the angles must be the same because they come from the same triangle, and they're all proportional. Right, and as a general rule of thumb, if it's a triangle inside a triangle, most of the time they're all similar. Again, most of the time. Okay, so let's use this missing information here to find the missing side length. Right, so we did a similar problem last lesson. Right, because first of all, we are not given a scale factor, but we can easily find it. Right, so again, our crucial piece of information is that we know that they're similar, right, because of this squiggly line. So let's give our triangle coordinates names, so it's easier to refer to them. So what's the scale factor? Right, the scale factor is right here, right? AB over DE, which is 2 over 6, reduced to 1 over 3. Okay, so very important here. Remember with scales, it's the image divided by the actual. Right? But with similar triangles, it actually doesn't really matter which one's the image, which one's the actual, as long as we keep the same order. So in this case, we're doing triangle 1, AB, right, over triangle 2, DE. So when we do our next proportion, right, involving the x, we're doing AC over DF. Right, which is 5 over x. Right? So from here, we do our the cross multiply butterfly. Right, 1 times x is x, 3 times 5 is 15, and then you're done. Okay, because again, be very careful here. Always make sure they are in the same order. Right, because what I could do also is say dE over AB, which is 6 over 2, which is 3. Right, and now if I do that, we have to do dF over AC, x over 5. Right, and as you can probably tell, we'll get the exact same answer. Right, because if, right, so we have 3 equals to x over 5. Right, we multiply both sides by 5, x is 15. Okay, so make sure that we are orienting ourselves in the correct order. Alright, if we get AB over DE, right, if we do DF over AC instead, we get 1 over 3 equals to x over 5. That'll get us a completely different answer. So be very careful of that. Okay, next question. So right here, right, this looks a little cursed, right? But they are still similar. And like the example we did earlier, right, we always have to make sure that the triangles are flipped in the correct orientation to actually compare the two. Okay, so what we can do here, let's flip this triangle so that's it's in the correct orientation. Right, because you can think of this triangle here. That's the nice thing about technology. I can actually show it to you pretty easily here. A, B, C. And 5 and 6. Right, so this is the top triangle here. If I were to rotate this, like this, right, now it's in the correct orientation. Right, and of course all my texts are backwards. Right, so as you can see here, let me just make everything right side up. Right, the 5 is up here, and then the 6 is over here now. Right, so I'm physically just rotating it so that both of those triangles are not in the same orientation. And then from there, there's business as usual, right? We're looking for y here, but we don't know the scale factor. But luckily we actually do. Got 10 here and a 6 here. So it's this. Let's take this line over this line. Again, doesn't matter the order, as long as you keep it consistent. So line CE over line CB is 10 over 6, reduced to 5 over 3. And then line CD over line CA, or AC. We usually write it alphabetically. Actually, doesn't really matter, but it just looks nicer. Okay. From there, we do our little cross multiplication butterfly. We should give the butterfly a name. dy. 2 times y, 3y. 5 times 5 is 25. Divide both guys by 3 to isolate dy. So y is 25 over 3. Cannot be reduced. Or 8 and a third. Okay, that's it. Okay, so always make sure to orientate yourself. Okay, here's the harder ones. Right, so luckily, as you can see in all the examples here, it's a triangle within a triangle. So they're actually all similar. Without really have to check the angles and everything. Okay, so let's find our two triangles. We got a small one here and a bigger one out here. So here's the big one, and here's the small guy. So that's 3 and 6. Now for the big one, as you can see here, the length is down here, which is 4 plus 6, 10. Give them names, A, B, C, D, E, F. Okay, so let's go AB over DE. Which is just A over 3. We don't know what A is. Next is BC over EF. Reduced to 5 over 3. Okay? From there, A over 3 equals to 5 over 3. Okay, 3 times A, 3 times 15. Divide those guys. A is 5. Alright. Okay, next, as again, reorientate ourselves. We got this triangle here. And we got this guy here. And we got this triangle here. And we notice here, both of them actually same the shear side of M. Okay, and then it's giving us all of our points already, so we gotta keep it. Alright, so we got A, D, C. And our second triangle is this one. Alright, so again, we are not doing this big triangle here. Alright. We are not doing this big triangle here, because to be honest, it doesn't really help us. Alright, so this is also about picking the right triangles, right? Because this big triangle here, I mean, yes, we know this length, that's 26, but that's it. We do not have this length and this length. We cannot use any of this information to help us solve for M. Okay, so, and then the smaller triangle. Okay, let's put the right angle sign here, just so we're not getting confused here. Right, so again, we rotate this guy to be like this, right? So that's our second triangle here. With 8, oops. 8 here, M is right here. Okay, cannot forget about our points. That's D, B, and C. Okay. AD over CD. Okay. DC over DB, or BD. Oh, sorry. CD over BD. Cross multiplication butterfly. Right, so M times M is M squared. 18 times 8 is 144. How do we find that? We square root everything to get M equal to 12, right? We square root everything here. Right, so remember, technically it is positive 12 and negative 12, but we cannot have a negative side length, so we just take the positive 12. Okay, so here's an actual pretty hard one. Okay, so we got two triangles here, right? And this is telling us how to orientate those, right? Because we have a line through those angles, that means those are the same angles. So we have to rotate them accordingly. Okay, so we got our big triangle here and our small triangle inside there. So that big guy, that was this angle here. That's A, B, C. We got 12 here and the length of n plus 6. Okay. Next is this angle here. We got 4, 3, and 6 right here. Alright, DCE. Alright, we grab this. Oops, that's copy paste. We will grab this, rotate it so that the corner is up here. Alright, so in this case, we notice here that no matter where you rotate, it's actually we don't really get the right orientation that we want. Alright, so in this case, we actually also have to like flip it. Right, so you can think of it as, can I flip on this thing? I actually don't think I can flip on this thing. Let's see, handwriting, take screenshot. Oh, yes, okay. So, yeah, so in this case, we can't really rotate it, right, to our current orientation. But you can think of it as literally like peeling it and then reflecting it. Right? Oh, I don't know how to draw this out on a screen. But you can think of it as taking the D and then flipping it to the bottom here. Right, you can think of it as flipping the D to the bottom there. Right, and then the angle gets flipped to up here. Right, so we're literally like bringing it down and flipping it like this. I hope it makes sense on camera. It's probably easier to show in person, but right. So we flip it down like this, right? And we know that this long diagonal here, right, is 6, right? Because this is the line that's opposite to the D, right? And then from here, we know that we flip it. Those are the points that we're working with. Again, sorry, I didn't really think this. I don't really know how to explain it on video, but it's easy to show in person. I'll just like put a piece of paper. Okay? And from there, we get our similar triangles. Okay, we got AB over ED. Sorry, DE. Again, doesn't really matter, but I'm gonna do it just because it's good practice. Okay, and next, BC over DC. Okay, and those are equal to each other. So we flap our butterfly wings here. Right, so 3, right, it's the same thing as 3 over 1. It'll be easier to illustrate that way. Right, n plus 6 times 1 is just n plus 6. What the? And then 3 times 3 is 9. Subtract both sides by 6. And just say is a good old 3. Okay, yeah, B. Okay, here's the last one. Word problem. Of course we can have word problems. Right, so we have a tree. So I got ground here. We got a tree that casted a shadow of 8 meters. Right, so that's 8 meters here. And we got a pole that's 1.5 meters tall and a shadow that's 2 meters long. Now so you can think of a sun as coming from here. And then we have a pole here that's 1.5 meters tall and it casts a shadow of 2 meters here. Okay? Or actually, it doesn't really matter. It doesn't necessarily even have to reach the end. It could just be like around 2 meters here. Okay? And now we know we could draw it like this because we are assuming that the sun's rays create similar triangles. So you can think of a sun rays shining like this. It's not very straight line, but right. So this is how you can see you got similar triangles here again. Right, the rays hits the things so that both of those are similar triangles. Right, so we get our 2 triangles. So this is the pole, right? 1.5 tall and 2 meters of shadow. And then we want the height of the tree, so we don't know how high this tree is, but we know that its shadow is 8 meters. Right, and then from there, right, 2 over 8, 1.5 over x. From there, we just solve as normal. Right, so 2 over 8, we can reduce that to 1 over 4. Right, actually here, let's keep it 2 over 8, because to be honest, it doesn't actually matter. We just cross multiply anyways. So it's 2x equals to 12. I divide both sides by 2. X is 6, or more specifically, meters. Alright, and yeah, you can see here, if we reduced the 2.2 over 8, right, if we reduce the 2 over 8, we get to skip one step. Right, cross multiply here is x equals to 6 right away. Right, so again, you don't actually have to reduce it if you don't want to, but just always have to just remember that it will be to do an extra step later. Okay, but that's about it for today. Right, so again, this is like the meat of the unit. Right, the whole point of why we care about scale factors so much is because of this. Right, we can use scale factors to find missing side length. Right, so always remember, whenever we're looking at triangles, always want to flip them into the correct orientation. Okay, so with that being said, good luck practicing.